Hello students, welcome back. So in my last class, I was discussing infinite well potential. So we have seen if my particle is trapped between two walls where the length of the well is 0 to L, one-dimensional well, and here you have a rigid wall. So V is infinite here. That means particle cannot move or escape from the this one-dimensional box. And we have calculated the wave function and energy eigenvalue permitted in this well, and we also discuss the symmetric potential, and we have shown whenever potential is symmetric. So if potential is symmetric, say I put 0 here and I make this box now from minus L to L. So we have seen if the potential becomes symmetric, the energy eigenstates have a definite parity. So they can be either odd functions or they can be either even functions. So let us calculate now the eigenfunction for this symmetric infinite well potential of length 2L. So we have already solved. Say this is the region 1, say this is the region 2, say this is the region 3. So here we have already calculated, here wave function will be 0 because here potential walls are infinite. So particle cannot escape. So here find the probability of particle is 0 here. Similarly, I take psi here also 0 because here we cannot also find the particle. And in between the here there is a no potential. Potential is 0. So we have seen that if I solve the Schrodinger equation for V equals to 0, because we have a time independent Schrodinger equation, say 2 del psi upon del x square 2m upon h cut square m h cut square, say 2, you have d2 psi upon dx square plus 2m h cut square e minus v psi equals to 0. And if I take potential here 0, so this equation I can write as a d2 psi upon dx square k square psi equals to 0, where my k is under root 2m e upon h cut square. I'm taking v0 in the regions 2. And now we know the solution, well-known solution of this equation is just a simple harmonic motion equation. So the solutions are for this equation a sine kx plus b cos kx. These are the solution of this equation. Now we can put the boundary values, boundary value, the continuity. We can find the continuity at the boundaries. So at x is equal to minus L, psi at x is equal to minus L is 0. Just put it 0 here. So this will be 0. And you put a minus L here. So this become minus a sine KL plus b cos KL. Similarly, if I write at x is equal to L, there also psi 0, and now this becomes sine KL plus b cos KL. Here I put minus KL, cos minus theta is cos theta, so here no negative sign will come. So now this is two equations. If I add these equations, so what will give me adding this equation? So adding these equations will give me 2b cos KL equals to 0, or you say b cos KL equals to 0. Now this tells me either your b is equal to 0 or cos KL equals to 0. So these are the two conditions. Similarly, if I subtract these equations, then this will give me minus 2a sine kl equal to 0. Okay, so this we got by adding. Now if you subtract these two equations, subtract, so this will give me what? This will give me minus 2a sine kl equals to 0, or you say a sine kl equals to 0. Now this suggests either a equals to 0 or sine kl equals to 0. Sine kl equals to 0. So first, let us say a0. Okay, say a0. So no point to see this one, because function is what? Function is your psi x is equal to a sine kx plus b cos kx. So if a0, this part completely becomes 0. So if a0, then what? We can go here. We can go here. So either b is equal to 0 or cos scale 0 equal to 0. So we already told a 0. So if we take b also 0, then this has become 0. Psi becomes 0. That is not normalizable. This is a trivial solution. So we will not take b equal to 0. Well, then we'll take cos scale equal to 0. So say a equal to 0. So b will not be equal to 0. Otherwise, function will become 0. So what for we are solving? So this is also not equal to 0. So cos kl 0. So cos kl 0 and cos kl 0 means this should be equal to say 2 n dash minus 1 pi by 2, where I'm taking n equal to 1, n dash equal to 1, 2, 3, 4. Okay. Now, so this is my so this become, if I have to n equal to 1, then this becomes pi by 2, 2, then 3 pi by 2. So now if I say my 2n minus 1 dash is, say if I say this is n pi by 2, if I say this is my kl is equal to, or k equal to n pi by 2l, then here my n will become, now say when n dash is 1, so n is 1, when n dash is 2, so n will become 3, so this become 1, 3, 5. So now my k become n pi by 2l, n equal to 135. So then my solution will become, so my solution psi x will become cos b cos k is n pi by 2l. So 2l. So this will be my solution, and where n is your 1, 2, 3. Sorry, n is your 1, 3, 1, 3, 5. So these function have a even parity. So this function has even parity. Similarly, if I take second case, I say my b is 0, then a cannot 0, then a cannot 0, that means sine kl 0. So sine kl 0 means you have, say, n dash pi, where n is equal to 1, 2, 3, n dash 4. So my k psi n pi, this psi n dash pi. Okay, similarly here, this is equal to kl here. So kl will be, now k will be here n dash pi upon l, and now I write this as a 2 n dash pi upon 2l. 2 n dash I take again equal to n, so this become again n upon 2l, and where n now becomes this n dash is 1, so n become 2, 4, 6, 8 even. So now my wave function will become So my main function will become psi x will be a sine n pi x upon 2l, where n is now 2, 4, 6, 8. And now these functions are of odd parity. Sine is odd parity function. Sine minus x is equal to minus sine x. So these are odd parity function. So that means now if I normalize these two functions, so it will, you can check, this will come 1 upon root L. Okay, A and B is root L. So now finally I can write the wave function for symmetric potential. If my wave function is symmetric, so symmetric potential, I can write that my wave functions are, say, 1 upon root L cos 2 pi, sorry, cos n pi x upon 2L, n pi x upon 2L, where n is 1, 3, 5, 1, 3, 5, so on, or psi x will be root L for sine n pi x upon 2L, 2L. So n will be 2, 4, 6, 8. So this will become my wave function. So if I want to take, say, ground state wave function, so ground state wave function will be, now let me first write the expression for energy. So K value is same for both the things, 2L. So energy I can write here En equal to the same expression what we are written for infinite spiral potential, because not symmetric, n pi square h cut square 2m. And now this time you have length is 2L, so this is 2L square. So this is my energy. So this energy will become now n square pi square h cut square 8m L square. Now let me write it solid further. So now if I find, say, if I find the energy, let me check the energy expression is correct or not. So yes, energy expression is h cut square. Yes, correct. N pi upon 2a square, 2l square, n pi upon 2l, correct. So now let me write the ground state wave function first. So my psi 1 will be the sine n 1 upon root L cos pi x upon 2L. This is my ground state wave function. And this energy will be, just keep it here 1. So energy will be, E1 will be pi square h cut square 8m L square. Similarly, if I now take psi 2, then we have to use this expression. So my first excited will be sine n is 2. So again pi x upon, so 2 to cancel and pi x upon L. If I put n equal to 2 here, so 2 to cancel, pi x upon L, and the energy will be E2. So it will be 4 of E1. So this will be, energy will be 4 of E1. Similarly, I can write psi 3. So psi 3 will be what? Psi 3 will be 1 upon root L cos of 3 pi x upon 2L. And the energy will be E3 will be, you can use same expression 3, 9. So 9 E1. So in this way, we can keep on moving. So these are the eigenstates for symmetrical potential which are with a definite parity, order even. We will discuss more about more about this. We'll solve some problems also in our coming classes. So I'll stopping here. Thank you very much.